So in this lecture, we will talk about the two-dimensional potential flow. We're going to take all the concepts we learned in the previous lectures and we apply them to a two-dimensional case. We will not be redraiving everything. We're just going to simplify the equations. What are some of the applications of the two-dimensional potential flow, especially in aerodynamics, is the airfoil, as for an example, for an airplane, right? So you have the airplane, and we want to know what the flow looks like up and down, right, around the airfoil itself. And that's how we use all the concept of circulation, vortices, and potential flow and put them all together. Because at the end of the day, what we really would like to do is predict what the lift is and what the drag is. And potential flow is nothing else than a mean of taking how I can represent a vector, right? A vector field, a velocity field that has a v, that can represent that by using a scalar. So if there's a possible way to find a scalar that will meet the certain conditions, then that scalar will be just enough to find my velocity field, okay, around this, let's say, airfoil. Um, so that is very helpful. And some of the, like for an example, a typical case could be you see this simulation that was done. This simulation is flow around a cylinder without any source inside. Okay, so there's the Q is equal to 0. There's no sink source inside here. And what you have this flow going all the way around this. And the way we can do this is actually through potential flow. But we will do this example. We have done a couple examples on this previously, but in this lecture, in the example we will do at the end of this lecture, we're going to learn where those equations actually came from. Okay, the couple of differences that is worth to point out. One is the phi, and the other one is psi. Right? This is a potential flow. These are the equations for potential flow, and these are the equations for streamlines. I'm sorry, stream functions. Okay, so although they all they lead to your velocity, right? But the relationship in both of them are quite different. First of all, when you differentiate this with respect to the same direction, this one differentiates this respect to the same direction of the velocity. This one is a differentiation in the direction normal. Okay, this is same direction. This is the normal direction to the velocity. In this case, velocity potential is specifically defined only for irrotational flows. Here it can be irrotational or rotational. This generally can apply to 2D or 3D. Stream function can be defined only for two dimensions. So they have their pro and cons, and it's worth that you take a moment, you pause, and you take notes on this chart here. So let's keep on moving. We did this last time, so I'm going to move a little bit faster here. You can take a pause. You can take a screenshot of the screen as you wish. So there are a couple of things. First of all, if I had the flow in the x direction, so my velocity is going in this direction, okay? This is the direction of my flow. Then my gradient vector is actually is given by this equation right here. It's given x and phi. And we did that previously, right? Now, if the flow is in the z direction, where this is the z direction, then note the difference, the change in the difference. Now, my velocity vector, now this is theta, now this is z. So this is saying is z, theta for z here, okay? So this is how this actually changed if the velocity now is in my z direction. This is important because different textbooks and different applications and different softwares use different notations. Some assume that the flow is going to go along the x-axis. The other is going to assume that the flow goes around the z-axis. So the equations They are identical actually in a sense, but they change limited variables. So just be cognizant of that as you move along and you know you navigate later in the future using these equations. Um, Now, as we spoke already, right, the most general case, the rotational flow. So if this coming in the x-axis, you have this. You can see this is phi. If you're working along the z-axis, then this remains the same. What you're going to change is the theta, theta, and z. So really, it's going to depend on the direction of your flow. Um, okay, so this is the velocity components for irrotational flow. That's just the fact that we have a potential flow. We should know that the flow is irrotational. Okay. Now velocity for a symmetric flow. Let's see what happens for asymmetric flows. Are flows where they don't have to be necessarily irrotational. Okay, and then some examples, basically axisymmetric problem is nothing else than a three-dimensional problem. Think about this case. Think about that. I have a cylinder. I got a flow that's actually, I got a flow in the cylinder. And what we are saying is, it's enough to actually model half of that. It just model the strip for which when I rotate this produces the cylinder. So in that sense, your analysis is really a two-dimensional if you think about it, right? This looks like two-dimensional plane. It's in a sense it is 2D, but it's also a 3D because actually it revolves this over the cylinder to make it a three-dimensional problem. So we have many applications for this. We can have an application in case that you have a cone here, right? So if I was going to do this, it's just good enough to take this, uh, model this as a two-dimensional element, okay? And then if I rotate this whole thing, I know it's going to produce I can rotate this, and that's going to give me my revolution about this axis will give me my three-dimensional model. You can think for an example, this case. This is a case like for an example for a jet engine. A jet engine, if you look at this, I can really just this is good enough just to use this model right here. I can just use this model right here that goes from here to maybe here. This whole thing is just good enough to model that in a two-dimensional setting, and that goes we revolve that, and that's a three-dimensional real. I'm really solving a three-dimensional model because the revolution of this it actually gives me a three-dimensional surface, three-dimensional volume. Same thing here. If I want to analyze what happens to a sphere, it's the same thing, right? I can analyze what happens to a circle. Because if I rotate this about this axis, right, if I rotate it, that produces a sphere. So many problems can be simplified by doing that. And there are quite a few problems in fluid dynamics, computational fluid dynamics, that we actually simplify everything because it makes our life a lot easier. So to understand a little bit how this really works, first of all, remember the ideal flow equation is this is ideal flow. So your continuity equation is equal to 0. In other words, the flow is irrotational, and it's also is incompressible. Because it's incompressible, that's why we take alpha equal to 1. And this is a direct consequence of what we have been talking about, right? So direct consequence of what we have been talking about. So the flow in a two-dimensional setting, then basically this is how phi and psi are related to each other. Okay, so if I have a flow going in one direction and I take the cross product, that's going to pull me the flow going in the direction of the flow. This is the direction in which this will be the direction in which your velocity is actually going to go. Okay, direction of velocity field, the gradient. Okay, so a couple of things we want to do here, and we have done this already. Don't want to spend too much time, but I just want to tell you that once I have my flow direction, one of my stream functions is automatically going to be that direction. Okay. As for an example, in this case, I'm assuming it goes in the z direction. So I am psi1, psi2 will be z. I know that. Now, what I'm going to do is, if I take, and then I want to find what this psi is, how I find such a psi, then I can just go ahead and say your velocity vector is equal to psi1 times psi2, where psi2 will be the flow direction. So in other words, if this is the case, you can show that the gradient of psi2, the only thing that remains, let me write this down here, another color, uh, that the gradient of psi2, the only thing that's going to remain is actually partial of z, partial of psi2 respect to z and k, because this is not a function of anything else. And this actually, partial of this is 1, so it gives you k. So this is where this k comes from. Okay. Now, this psi1 is just a general stream function psi. So when I took the partial, I take this cross product, this produces this, and by relating this, you can see what your u is equal to this term and your v is equal to this term with the minus sign, obviously. So we can take this is plus, put the minus there if you want to. So that's easy to see there's a minus sign involved with this. So if I was going to just take the gradient of this, now the absolute value for this, right? Then what I would get is the same thing, something similar to what I had for potential flow. But this is for streamlines, okay? This is not the potential function. This is the streamline function. Okay, so now for the symmetric flow in cylindrical coordinates, let's assume that we're working in the x direction. I will tell you what equations change later. In the x direction, then if I'm flowing in the x direction and it's axisymmetric flow, so one of my stream function immediately is going to be phi, but it's an axisymmetric. So if I did that, this was the case I'm working with, and psi1 was equal to this, psi2 is equal to this, and take the gradient, and you can see that the gradient of psi2 will be nothing else than 1r e phi. You can show that. You can do this whole derivation for yourself, and you can show this is what you get. Okay. And then if I keep expanding this, you can find this is equal to this. So I find my UR is equal to this, U phi is 0, and UR is UX is equal to this. Now, this is if I'm working in the X direction. If I was moving in the Z direction, and again, we have done this lots of time in the class, several times now, so I'm just capturing a few thoughts here. So just want you to know that now if I move in the Z direction, this is theta. What changes here, right? That the Z instead of X becomes, instead of X, it becomes Z. Instead of phi, it becomes theta. So those are the major changes here. And the final answer then again is the same, right? What's going to change here is just the letters. So it's not a really big difference in what axis you work with. Okay, so let's see what happens when we have constant vorticity, right? So when I'm saying a constant vorticity, we know that your rotation, your vortex vector is going to be constant. That's not going to change with time. It's not going to change with spatial direction, sorry. And so in that case would be constant. So let's assume that your flow is going in the x direction, okay? This is your flow. I'm sorry, it's invariant in the x direction, so there's no flow in the x direction. Everything is bound basically in my r and phi direction. So in other words, what I'm going to really have in this problem is I have r, and phi, nothing else. Okay, everything inboard, outboard will be 0. Okay, so now I move on. So the flow rotates about the origin. As it's rotating, you're going to have a vector r, and you're going to have this. So, and this is the direction of ER. This is the direction of ER, if you would, from here to here. Okay, in the same direction of the flow of R. This is Phi. So then if I go ahead and do your find your continuity equation, and I do that, you can see that this has to be zero because the flow is rotational. So if I did that and I did this variation, now you can see if you go back here, this is U of phi, okay, it's right here. That's where this comes from. So I got U of phi respect to phi. This is U of r respect to r will go to zero. So then you basically end up with saying that this is a pure function of is equal to zero. So you're basically saying this is going to be a constant in r. Okay, so if I did that, I know that's a constant in R, and apply the cross product to this now, and we apply the cross product, we get this value, and we expand all this, and you can just show that this is the same thing from here as well, right? You know that this is going to give you your rotation. So there's nothing else. Is I'm working about the e-axis, x-axis, so this will be omega I. Okay, you know that. So basically, I can take this equation now. I can equate these two. Okay, so this where this comes from, again, this comes from the cross product, right? So if I do this cross product in the polar coordinates for this particular problem, this is equal to this. But I know that the curl of V is actually going to equal to your vorticity, right? In this case, in the x direction. So you know this has to be a constant. So if I basically integrate both sides by r dr, you can show this is equal to this. This constant would be zero because by applying the boundary condition at the center, I don't want to have any vortices right in the center. So when I do this, then you find your phi is equal to omega over 2 r. Note that omega over 2 is nothing else than uh, your rotation. Okay, this is vorticity, this is rotation. Okay, so this is the rotation rate. So your rigid body rotation is given by this. Remember, we're working in cylindrical coordinates. So working a two-dimensional, but it's axisymmetric. So this could be a sphere, as for an example. So what we are saying here, or a cylinder. So what we are saying here, if you just apply all this, your V is actually equal to this. And then I just replace all the values. You find that your total rotation is actually equal to pi omega r squared. So this is how your velocity with respect to the radial velocity goes, right? Is zero in the center, and it moves like this to your maximum radius A. Okay, and that's going to give you your maximum possible velocity u phi. Now, this is the velocity that's linear, but your circulation is actually quadratic in its nature. So if I have a value here, A, that's the probably maximum rotation you can have, your circulation you can have. So if you do this, then you'll find this will give you some sigma, your gamma max, maximum possible rotation. Okay, so it's important to understand the relationship between the velocity, between the speed and the and your circulation. Okay. So now let's see what's going to happen here with the circulation in two dimensions. So the irrotational flow with circulation for 2D. So we just found that this was equal to U phi, E phi, okay? Then from here, we also show that this was only a function of R. And we also show that when you take the cross product of this, you found that this is equal to 1R partial of R respect to uh, R U phi I is equal to 0. So from here, you can show that partial of R phi has to be 0. So I can show that R times phi is actually equal to a constant. Okay. In other words, this is going to equal to K over R. Okay. So that means that your velocity field would be K over R E phi, and this is what we know as the vortex flow. Okay, because it comes from the equation of vorticity. So now, if I'm going to find the circulation around this, so we know that your equation of circulation is given by this, and this is V dot L, goes from 0 to 2 pi, and this is KR. This would be R d phi, okay? And that will give you, the whole thing will give you 2 pi K. Um, and then, because you know that this is, by the way, this is equal to R d phi E phi, okay? So then your circulation is equal to 2 pi K. Then I can go ahead and say the value of the K that I'm looking for is circulation 2 pi. And you can see the velocity field I got here, right? I can replace that in there. And you will find that you get the following value. So you can show that your velocity then is going to be 2 pi r E phi. Okay. In other words, U phi will be gamma 2 pi r. Okay, so we are basically trying to say here is that what you can immediately see from this equation, right here at the center, right, we know that your vorticity cannot be 0. Your vorticity is not 0, or it can be 0, right? If this is 0, then your velocity will be 0. If it is not 0, then your velocity. So right here in the point is there. Here your vorticity will be is irrotational. So here will be 0, but not at this location right in the middle. Okay. So if I'm going to plot this, so let's see so there are a couple of things that you have to know. This is what we know as the ideal vortex flow. This is the dream. This is the dream come true. So you have this, you have R, you have U of phi, and then you have this equation. This is what the equation actually looks like for U phi um, is equal to gamma 2 pi r. Okay, this is the ideal vortex flow. Now, what is true is that if I'm going to go ahead and plot now if you look at what happens here, right, based on this equation right here, uh, we can show that. So if I have my cylinder, right, and I go to my radius r, where my radius r ends in a. So what I'm going to tell you is, if this is my circulation will probably remain constant until I get there. Okay. So this is nothing else than your circulation 2 pi k. However, what happens here in this region here, as I get close to r equal to 0, okay, in this region where r is equal to 0, so it's the center of the cylinder, in this region, it can be anything. Uh, so it could be something else. Okay, so for this, we have several things that we can possibly do. We got what we call the Rankine Vortex method. In the Rankine's Vortex method, your phi was actually equal to omega over 2r, right? So you can draw this straight line and you can show that everything, the area, shaded area here, for that shaded area there, your omega is actually not equal to 0. It has a value. The area under this will actually give you a value uh, uh, for your circulation, for your vorticity. Okay, so then this will have a straight line there, and it will go, straight line from here to here, where they intersect. It comes here. So, but however, we can also do the following: combine these two equations. If you remember this equation, right? That we showed you that your equation was, this is the velocity and this was the circulation, right? Using that equation. So we show you that once you get near x equal to 0, right? Once you get close to x equal to 0, whereas r sub 0 is near r equal to 0, it's not r is to 0, it's just near that value. So distance is very small. Exaggerated this for this purpose of this illustration. So this may look something like this. What you really have in real life, your vortex is actually neither like this, neither like this. It's actually something along this line. Okay, this is your real vortex. The other are idealization and approximations that we use to simplify our analysis. Okay, so now I want to go back to what we talked about previously, stream functions. We had talked about stream functions, but let's specify the stream functions only for a two-dimensional flow. So far, we have talked the general stream functions. Now let's make it more specific. So, say working axis symmetric plane, let's say this is the xy plane, or a two-dimensional plane, xy plane. So in other words, I'm not going to have a velocity in the w direction, so this can go away. We talked about that when we talk about stream functions. So by definition of a streamline, when I take this cross product, this gives me 0, right? So dx is divided by u, dy divided by y is equal to dz divided by 0. And your problem is basically saying in this problem that this is 0 because w is 0. If you remember back, we talked about this. So I'm moving a little bit faster here because we have done this discussion before. So again, this is about the z-axis, okay? So we are confound your two-dimensional x and y, so this is the other axis. So if we just find this equation now, you can show that this whole thing equals to this. And note that alpha is equal to 1 for ideal flow. Again, we have been doing this several times. And then we also have done this before. This is to satisfy the conservation of mass or continuity equation. Then in polar coordinates, if you're going to do the polar coordinates, it looks like this. And the final answer then, polar coordinates, that's really of interest. These are the answers that you can basically say this is equal to, and your continuity equation is equal to this and has to be 0. Okay? So let's recap everything we have done. First, when we say incompressible, we are talking that your volume cannot be reduced, or the continuity equation is equal to zero, right? Your mass conservation is zero. When we say it's irrotational, we are saying that your vorticity is zero, right? There is no vorticity, so vorticity is equal to zero. When I say inviscid flow, I am saying there are no viscous forces because of shear loads, okay? In other words, if you remember, we talked at the beginning of the classes as du dx, right? So we are saying this is, I'm going to ignore all this, and we're going to say this is very insignificant, and that can be basically equal to zero. But if I do that, I am staying away from what happens around the wall, right? So I am studying, so this immediately, the consequences of this just tells you immediately, if I have a wall here, right? Around this wall, I am, because my flow is coming in this direction, and I'm going to, this is flow is going to try to create vortices around here. And therefore, I'm going to have a real, your shear components. But if I move away from this, right, I move away from my boundary layer, where everything I can assume that's basically constant, right, this uniform flow. Here I don't have any rotation. Here omega is zero. Okay. Here omega is not zero, right? Close to this in the boundary layer, it's not zero. Outside the boundary layer, it is. So that's where we are really analyzing and studying all this. Okay. So then this is all mathematics. This is all equal to zero. You may want to pause this and take a nice shot of this and write this. This is a nice summary of how everything actually works. This is because of continuity. This is because of its rotational. Okay, they are not the same. Okay, although they look like the same, you have to know that this comes from the fact of continuity equation. It comes from this equation. Okay, and this comes from this equation. Okay, both are derived from two different means, although they look alike. Okay, in Cartesian coordinates, this is what they look like. At the end of the day, what you're going to have is, at the end of the day, in the z direction, if it's polar coordinates, you have something like this. And u theta is this. And remember, it could be u phi if it's in the x direction. And in general sense, this is the equation that the equation that it comes from for the potential flow. Just to wrap up the discussion here at the end, there are a couple of things that I want to point out here that's important as well. So if I have a line integral, right, that goes from A to B, and this is my velocity vector, then going around this vector right here, if I take the dot product, I'm really taking the projection of this here. So we are really taking that projection, we're taking a dot product with that. And then when I do this, I can show that this is actually equal to this. So the value of my potential at point A, my value of my potential at point B minus point A. Let me just show you this, just so you can really understand where it comes from. The couple of consequences, you can see that your potential, your potential flow will be a multi-value, so you can have more than one value if your circulation is present. And you can see this from you can see this from here, right? Because if I have this and I'm using the potential flow, v dot nds, I just showed you this is equal to phi at b minus phi at a. And if my circulation is equal to that, if this is equal to zero, then it's not multi-valued, right? That means my function has the same value everywhere. Multi-valued means that doesn't matter If I'm here, I'm going to have a different value. I'm there, I'm going to have a different value. Here, I'm going to have a different value. As I move along the path, my potential can have different values. But if it's equal to 0, okay, uh, different values, if it's not 0 and it's equal to 0, then it's going to have the same value. So it doesn't matter where you're standing, it's equal to be 0. Okay, so that's important. The same consequence, if you can do this using streamline function, this is also true. Remember, all this is true for a net flow coming from or going to the region to be 0, but we will discuss about these things later in the course. So two-dimensional flows, how they work. This is the proof. So I got this right, where ES is going to be this direction. Really want to at least show you where it comes from. So this goes this, and where this is actually equal to, this is where V comes from. So you take the cross product with that, and then this gives you ES, and this is equal to DS. So at the end of the day, you get this, and you can see that this is going to be equal to this if your circulation is 0. It's going to be different. It's going to multi-value if it's going to be different, just as a proof that you're going to indeed get the same answer as your potential flow. Okay? So want to wrap up a couple of this thought process here. So you can say that this is going to be multi-valued if this is not equal to 0. In other words, you can show that at B is actually equal at A. Is going to be single value if your circulation is 0. In other words, this is not the same, I'm sorry. B is equal to A. And the same is true, the same thing can be said for your stream function. Same thing can be said for your stream function psi, 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 and psi. Okay? This is important because when we try to model, when you're going to try to model all this, your two-dimensional flows, when you're trying to model your two-dimensional flow, you're trying to understand what happens to flow around the airfoil. It's very hard to actually model the real flow. What is the real velocity field? We don't know what it is. Have no clue whatsoever. So what we typically do in that case is we try to find potentials, and those potentials help us understand what happens. We know the potential don't apply when we are close to the boundary, but outside the boundary gives us a very good idea, and then we can use other assumptions to actually, other tricks that we can use to actually model what happens around the wing. Now, the potential flow greatly is going to help us to determine and approximate what happens with the lift equations, how much is the lift and the drag, and that's what we're going to see in the next couple of classes as well. So this wraps up our topic on two-dimensional potential flow.